This brief presentation will give you a clear understanding of quantum mechanics. How quantum concepts established the modern theory of the atom structure. You will understand how each electron defined by 4 quantum numbers creates shells and subshells for all the elements of the periodic table. The discovery of the electron, and the proton, was critical to develop the structure of the atom. In the late 1800s, J.J. Thomson, using a cathode ray tube, discovered the electron. The charge was determined to be negative, since the particle beam was repulsed by negative voltage. This led to the J.J. Thomson pudding model, in which positive and negative charged particles are dispersed over the entire volume of the atom. This concept of the atom was revised by Ernest Rutherford, a former student of J.J. Thomson. By bombarding alpha particles at thin gold foil, most of the alpha particles pass through the foil and strike the fluorescent screen. However, some alpha particles are deflected back. The alpha particles are repulsed by a positive charged nucleus, as illustrated in the animation. Ernest Rutherford envisioned the atom consists of an electron revolving around a positive charged nucleus, similar to planetary motion. The discovery of quanta. Classical physics estimates for radiation intensity as a function of frequency were not able to explain actual radiation behavior, as shown. Max Planck theorized that the energy radiates chunks of energy or quanta. By adding a constant to account for the quanta, he was able to predict the observed radiation curves. Albert Einstein embraced and utilized the quantum concept to develop the photoelectric theory. He observed chunks of light energy impacting metal releases, quantum amounts energy, which he called photons. The shell structure of the atom began, like the science of chemistry, as an entirely empirical, experimental science. Spectral lines for hydrogen were created by applying high-voltage charge to a Geissler tube as illustrated in this animation. The high voltage applied to hydrogen excites the low-energy state electron, to propel it to a higher energy state. When the high-energy state electron returns to the low-energy state, it radiates energy, a photon, recorded on photographic plate. Numerous physicists, at that time, attempted to develop empirical equations to predict spectral lines of hydrogen. Researchers Johann Balmer, Theodor Lyman, and Friedrich Paschen observed unique discrete spectral lines with increased energy levels. To explain the spectral lines, Niels Bohr embraced Max Planck's concept of quanta. He viewed the atom as electrons located at different distances from the proton, revolving around the proton nucleus, similar to the planetary system. The electrons at different energy levels, or quanta, are principal quantum numbers, designated by the letter n. These are integers, equaling 1, 2, 3, and so forth. Charles Barkla, the X-ray spectroscopy specialist, designated the electron energy levels as K, L, M, N, and so forth, to reflect the historic X-ray series performed. The Bohr model could not explain all the spectral lines. Spectral lines of other elements were observed, such as helium. Arnold Sommerfeld extended the Bohr model to explain the thin spectral lines, ignored by Niels Bohr. He viewed the principal quantum levels as thin discrete layers, like the shell of an egg, containing minor elliptical orbitals within each quantum level. These additional orbitals consist of a quantum orbital for its shape, noted as the letter L, and magnetic quantum, for orientation M, noted as M sub L. An additional quantum number was discovered when Otto Stern and Walter Gerlach directed a silver atom beam through a non-uniform magnetic field. The beams should create one spot on the photographic plate. However, the photographic plate revealed 2 lines formed. Samuel Goudsmit and George Uhlenbeck interpreted that the 2 lines are formed by 2 electrons spinning with opposite rotation, adding a 4th quantum number for electron spin. By 1925, the model of the atom consisted of electrons having unique 4 quantum numbers. The principal quantum number designates the energy level of the electron, which is determined by the distance from the proton. Within that shell, there are three quantum numbers. The orbital quantum number establishes the orbital's shape. The magnetic quantum number establishes the orbital orientation. The spin quantum number establishes the electron spin. Examples of electron configuration are illustrated when the principal quantum number is increased and the shell's respective orbital and the magnetic quantum numbers are calculated. When n is equal to 1, L is equal to n-1, or 1-1 equals 0. The orbital quantum number, L, is 0 and the magnetic quantum number, m sub L, is also 0. The electron orbital designation is S, for sharp. The shape and orientation of the s orbital is shown. If n is equal to 2, then L is equal to 1. M sub L can have three different orientations. The electron orbital designation for this electron configuration is P, for principal. The p orbital shape, and only the x-axis orientation is shown. The y and z-axis orbital are not shown in this illustration. If n equals 3, then L equals 2, and M sub L may have 5 different orientations. This electron orbital designation is D for diffuse. The shape and orientation, for d orbitals, is shown. As the principal quantum numbers increase, the shape and orientation become significantly more complex. In the case of n equals 4, L equals 3 and M sub L has 7 different orbitals, with an orbital designation, F, for fine. The complexity of the 7 different orbitals is shown in this illustration. Wolfgang Pauli determined that each electron is unique, identified by these 4 quantum numbers, and each orbital can only have 2 electrons. The shell and subshell atom structure is further simplified by placing the principal quantum number, n, in front of the subshell designation. When n is 2, then the subshells will have 2s, with 1 orbital in the subshell, or 2p with 3 orbitals in the subshell, with a total of 4 orbitals in the shell. When n is 3, then the subshell will have 3s, with 1 orbital in the subshell, or 3p with 3 orbitals in the subshell, or 3d, with 5 orbitals in the subshell, with a maximum of 9 orbitals in the shell. Let us review the shell and subshell notation for elements, used in the periodic chart, for the first 2 principal quantum numbers. Another way to illustrate electron orbital subshells is to use the box notation. Each box may contain a maximum of 2 electrons, and their spin. It also shows empty boxes for vacant orbitals in that shell. Lithium has 2 electrons in the 1s orbital, and 1 electron in the 2s orbital, with the 3p orbitals empty. In beryllium, the 1s and the 2s orbitals are filled, while the 3p orbitals are empty. In boron, after 1s and 2s orbitals are filled, then the first p orbital is filled. As the atom's number of electrons increased, Friedrich Hund developed rules for filling the orbitals. In 1925, Hund's Aufbau concept states that the electrons fill the lowest energy orbitals first, and then move up to higher energy orbitals, only after the lower energy orbitals are full. In addition, every orbital in a sublevel is singly occupied before any orbital is doubly occupied. All of the electrons in singly occupied orbitals have the same spin. In nitrogen, the p orbitals are half-filled. The 3 electrons in the 2p subshell will fill all the empty orbitals first, before pairing, that is, adding the second electron to fill the orbital. Oxygen with 8 electrons fills the 1s, the 2s and adds 1 electron, with same spin, into each of the p orbitals, then pairs the 8th electron into one of the p orbital axis. Fluorine with 9 electrons fill the 1s, 2s, Then the two electrons pair the two p orbitals as shown. Neon with 10 electrons fill all the orbitals, resulting in a noble gas, like helium, is chemically inert. In summary, the elements of the periodic table are grouped based on the 4 quantum numbers, filling the s orbitals, the d orbitals, the p orbitals, and the f orbitals.